Hi, so this presentation is about the accuracy of sample statistics. This goes with Module 4 in the OLI textbook and Module 4, Topic 14 of the workbook. And so statistical estimates come with some error, and much of what we do in the course is going to be about understanding how much error to expect. The error comes from two sources, but the basic idea is when you measure a continuous variable, first of all, you cannot measure it perfectly because a continuous variable might have many, many digits of accuracy after the decimal point. And so your device will be just limited in how closely you can measure the variable. Now, in statistics, our task, it's not just to measure the variable, but we're usually looking for a population parameter. So the population might be the set of all City College students. The variable that we measure about each student might be the temperature of the student. We might be trying to estimate a parameter like the mean or the median of the temperatures of all the students in the population, that is, all the City College students. Okay. How do we go about estimating the average temperature of all City College students? Well, we take a simple random sample of a few hundred students, and we find their average temperature. We get the sample mean, and we use it as an estimate for the true population mean. And so when we get this estimate, it will not be exactly right, and the error comes from the two different sources. One is that each individual measurement, the values of the variable that you get for each person, are imperfect. The measurements are not perfect themselves. That's called a measurement error. But there's another kind of error called sampling error. And that comes from the fact that we could not measure all of the students at City College. We randomly selected 100 of them. And tomorrow, if we selected a different group of 100, we might get a slightly different average because of having different people in our sample. So the discussion today is just about the measurement error. For the sampling error, this will be a probability kind of problem that we'll address later in the semester. Now, we're not going real deep into measurement error in this discussion. We're really just trying to decide when I write down my sample mean, for example, or I write down my sample standard deviation, or some other sample statistic, how many digits should I report? So we're only going to get so far with the discussion as to decide, do I write my data, my statistic down to the nearest tenth of a pound or the nearest hundredth of a pound? based on how accurate we think the original measurements were. So when you present data, maybe you've gone out and measured a bunch of things yourself and you have this list of numbers. You need to reveal to your reader the amount of measurement error that you believe the data has. So you can say that the result is accurate to within plus or minus some number of pounds. Or you can just limit the number of digits that you report. So you could write out all the digits and then say plus or minus a lot. Or you could just not write down the extra digits that you're not sure about in the first place. So you reveal the measurement error, you reveal the sampling error. Now this is easy. So when you calculate the sample mean, as you know, you just add up all the data and you divide by how many of them there are, and you get an answer. If I was taking the average of 2 and 3 and 7, add that up, I get 12. Divide by 3, that was the sample size, 3 individual datas in the sample. I get 4 for my sample mean, but it's not exactly right, because if this was a continuous variable, that 2 is not exactly 2, it's 2 point question marks, sort of. So the 4 is not perfectly accurate. And there's a standard for just how you decide how many digits to write down. If you're not going to talk about the whole plus or minus thing, and if you're not going to try to get real accurate about the accuracy, if you're just going to round off and decide where should I round, there's a rule for how you do that, and it's real simple. You report one more digit than the original data had. So to recap where we're at, when the data come from measurements of a continuous variable, every measurement contains some error. When you find the sample mean, you don't know the exact value of the mean, because each one of the individual variable values that went into the mean has error. So the digits at the small decimal places may be wrong. Now the standard is you can report one more digit than the original data had. Okay. So like if you had just 2 numbers in your sample, you had 4 and 5. You average those, you get 4.5, halfway in between. You're allowed to give that one extra digit. You don't round. You don't round all the way to just one digit. You say 4.5, it's halfway in between. But if you had more digits than that, if you had a couple of numbers, I don't know what, and you got 4.513, you only report one digit more than the original data had. So in this example with 2, 3, and 7, you do the sample mean. You can write down 4.0 so that your reader knows it did not come out in between 2. See, the original numbers here were reported to the nearest whole number. So your sample mean is reported to the nearest 10th. So it gets that extra 0.0 on the end. So here's some oak tree diameters. This data has 1 digit to the right of the decimal point. This data appears to be accurate to the nearest 1/10 of an inch. So when you report the sample mean, you'll go 2 digits to the right of the decimal point, 1 more digit than the original data had. So see how I went out to the hundredths place. I said 0.87. I included that 7 in the hundredths place. It might go on, the number on my calculator might go on farther, but I cut it off with 1 digit more than the original data had. So how accurate is the sample mean for this data? It's accurate to the nearest 1/100th of an inch, because the original data was accurate to the nearest 1/10 of an inch, or it's reported to the nearest 100th of an inch. Now this data has 2 digits to the right of the decimal point. This data is accurate to the nearest 100th of a milligram per liter. So the sample mean should have 3 digits to the right of the decimal point, just 1 more digit. Find the mean of the first 4 numbers, you add them together and divide, and you report 0.435 milligrams per liter, because you want to go out to the 1,000th place 1 digit more than the original data had. How accurate is the mean? Since the original data was accurate to the nearest 100th of a milligram per liter, the mean is reported to the nearest 1,000th of a milligram per liter. Now this data, these weights of football players, does not have any digits to the right of the decimal point. So it's accurate to the nearest whole pound, or the nearest 1 pound. When we calculate the mean, we're going to go 1 extra digit and go out to 166.3 pounds, because there's 1 digit to the right of the decimal point. So how accurate were the players' weights? Accurate to the nearest 1 pound, in other words, plus or minus half a pound. So the mean is reported to the nearest 1/10 of a pound, which is plus or minus 5/100ths. So the same rule about adding the 1 extra digit applies to several other sample statistics, most of the ones we know about. There's the mean, the median for measures of center. There's the standard deviation, the quartiles, and the interquartile range for the measures of dispersion. There are only 3 that are reported with a different rule from the others. You do not add the extra digit for the maximum, the minimum, and the range. The maximum is just the biggest value of the biggest X value in the list of data. The minimum is the smallest. The range is what you get when you subtract those two. And they don't need the extra digit. You never have to go halvesies to go halfway in between 2 data. So they don't get the extra digit. And that's all for this topic.